Section 6, we're going to talk about more rational functions and their applications. So the first part about this is about removable discontinuities. So we know the domain of a rational function is found by setting the denominator equal to 0. Therefore, there's an asymptote, or a hole in the graph, at x equals that value. An asymptote is where a rational function is discontinuous, and so for these problems, there will only be a hole in the graph because we can factor the numerator and it will cancel with the denominator, thus making it a removable discontinuity. So an asymptote, there's no way to change that, but with the removable discontinuities, you can plug the hole. So it's a lot like those piecewise functions we did in Chapter 2, Section 7. So for the example below, we have f of x equals x squared minus 9x plus 20 over 2x minus 8. And so if we factor the numerator, that would give us x minus 4 and x minus 5. And we can also factor a 2 out of the denominator. Thus, the x minus 4's will cancel, and we'll be left with x minus 5 over 2. Or if you prefer to write that in your slope-intercept form, that would be 1/2 x minus 5 halves. So that's the equation that we're going to graph, but we know from our original equation, the denominator, that x cannot equal 4. So if we graph our equation, we would start at negative 2.5, and then we would do our slope, so we would go up 1 over 2, up 1 over 2, up 1 over 2. And you could also go down 1 to the left 2. But we have to have a hole at that x equals 4 value. So x equals 4, if we plugged it into that equation, the y would equal negative 1/2. And so you can connect the dots and make a line, leaving a hole at that value. So to tie it into Section 2.7, if we wrote this as a piecewise equation, we would have 1/2 x minus 5 halves for all real numbers except x equals 4. And we would have negative 1/2 where x equals